Okay. Any questions? Okay, so let's start our lesson again. So we want to talk a little bit about product rule. The main goal is actually extending this product rule because there might be tasks that cannot be broken down to two tasks. Yes, we can. For example, if I ask you to write a 3-digit number, then of course I am involving 3 steps. Yes, the first digit, middle digit, and the right. Okay, so the first natural thing is to extend the product rule from tasks containing only 2 stages to tasks containing more stages. Okay, but before that, let me see that how do you solve this problem. So, example. So how many 3 by 3 squares? How many 3 by 3 squares are there in a chessboard? I think they call it checkerboard or something. Yes, am I right? Anyway, so you know, so chessboard is 8 by 8, including, I don't know, black and white small squares. And now we want to count how many 3 by 3 squares are there. Okay, so start thinking a little bit about that. So when I am just drawing this chessboard. All the squares should be identical, the same size, not identical.
Mr. Baba,
Yes?
do you have a chess kilo?
Pardon?
Do you have a chess kilo?
I don't know, there's a website. I sometimes play there. I sometimes reach to 1400 and then sometimes I go below. Yeah. I don't know, I forgot the name actually. That's a famous one called. Pardon?
Is it Lichess maybe?
Yeah, Lichess, I think. Yeah. Okay, so we want to count how many 3 by 3 squares are there in this chessboard, 8 by 8. So for example, this is one of those, yes? This is a 3 by 3, yes? Or I can have this one, for example. Right? Yeah, so here, for example. I can have this one. Okay, now we want to count all of these 3 by 3 squares. Okay, so what should we do now? Yes?
Look for how many valid x coordinates there are for a 3 by 3 square.
So let me just tell you something. Might be because this is completely open problem. You might have different strategies to tackle the problem, so that the burden is on you to defend your point of view. Okay. The way that I am thinking is that I am giving this as an example of the product rule. So it means that if I want to solve this problem, my strategy to solve this problem is using the product rule that we learned before. But for product rule, this is important, I want you to teach. If you want to use product rule, you need to have a definition of your task. You don't need to write it down explicitly, but you need to have a task in your head, and then split that task into different parts, here to 2 parts, so that the product rule is applicable, if possible. Might be you do all of these things and you see that, okay, a product rule is not applicable to this situation, or at least it is not the only tool is needed to solve this problem. So this is why I want you to get used to this way of thinking. And then, by the way, if you go to technical universities, you will definitely have a course. You will have a course on discrete mathematics. So it is very, very good to learn these things right now, because it will save you a lot of time in the future. So you need to give me your task. You need to think, okay? Because sometimes if I want to count all of them, so I don't know how can I divide drawing a 3x3 into two steps. So you need to have a strategy, if possible, to express this problem to an equivalence problem, so that it can be split into 2 parts or whatever. Yes, Alex?
I would say that my task would be to find a valid top left corner for the 3x3. So I would then
top left corner, you mean this one?
Yeah, exactly. And then
this is your task?
Yeah.
If that is your... Okay.
It has to fit. So I can't have H8 on the chessboard, because then it wouldn't fit inside it.
No, but so when you say that only you care about top left corner, I think that's right, yes? Because if you say that I am choosing the top left corner, so then it means that
there are 6 valid positions.
So top left corner, if the top left corner is clear, then we can draw the picture. It's clear, yes? For example, if I tell you that this cannot be the top left corner, yes? Because then it is not enough room to draw them. But if you give me that this is the top left corner, immediately I can draw my 3x3. So that's good. But why? So this is your task. Your task is to choose a point as the top left corner. Okay, but this task can be decomposed into 2 parts, yes?
Step 1 is find a valid x, and step 2 is find the valid y.
So very good. I think that's good. Yeah. My intention was not that, but your solution is better, I think. So yeah. So he's saying that so the task, he is defining the task. Let me just be explicit a little bit here and write them down. Okay, task. The task is this. Determining, I don't know, you can cook up a story for yourself. Determining the top left corner of the 3x3 square. Or whatever, this is not very important, okay? Okay, so now you say that, okay, I divide this into 2 stages, because if I want to choose a point here, how do you think about yourself? When I ask you to find a point there so that I can have this as the top left corner of my square, so immediately it is clear for me that no one will choose this. So this means that in your brain, you already know how you are deciding. So you need to split it up. Okay, so you are saying that stage 1, okay, can you tell me choosing, so let me, for example, this is the vertical direction, this is the horizontal direction. So what can I write for, can you write it for me, Alex? So what is the stage 1?
Choosing an x such that.
So let us, because everyone knows that this is the x-axis and this is the y-axis, so let us not make it hard. So choosing the x coordinates of the point of the, let me write it like that, top left corner, of the top left corner. And then stage 2, So do you agree that this is not still done? Because if the task 1 is done and I am left with nothing, my task is not accomplished yet, because I have just determined about the x-coordinate. If I say that the x-coordinate is 2, so this is the x-coordinate 2, but it is not clear I am choosing this point, this point, this point, or that point. So it is not accomplished yet. So I have to finalize the stage 2 as well. So I would say choosing the y-coordinate of the top left corner. So anyway, this is your task. You broke it down to 2 stages. Now, how many ways I can accomplish stage 1? I will call it N1. So this is the origin. Assume that this is the origin, and assume that this is your x-axis and this is your y-axis. So which points can be chosen as the x-coordinates of that? Can this be the x-coordinate? Yes or no? Yes. Yeah, in principle it can, yes, because you might start from here. So this can be the x-coordinate of that one, yes? This can be the x-coordinate. But which one cannot be?
The last two.
So yes, this cannot be, this cannot be, and this cannot be, but this can be, yes? So it means that these 3 points are, so how many choices I have? 1, 2, 3, 4, 5, 6. That's it. I have only 6 options available, yes? So this gives me 6. Is that understandable? So there are cases that I can choose every one of these points, but it is completely clear I'm not allowed to choose these points. But how many ways I can choose the y-coordinate of the top left corner? So can I choose this as the top y-coordinate? No. Yes? So it means that this can be chosen up to here. Yes? So how many one of them? So 1, 2, 3, 4, 5, 6 again. Yes? But here, you need to be careful. When you want to write this 6, this number should be independent of the way that you have done the first step. You need to convince yourself of that. If that is not the case, the product rule is not applicable. So is this true or not? Is this 6 independent of how I have done? For example, you need to convince yourself. I don't know how, but for example, let us concentrate on this point. If I have chosen this as the x-coordinate, can I choose this as the y-coordinate? Can I choose this as the y-coordinate? Yes, because I can build up my 3 by 3 here, yes? So this is possible. Can I choose this one? Yeah, it is possible. Can I choose this one? It's possible, yes? So it is clear that if I choose this one in the first step, I have every 6 options available. But do you agree that if I change this point to this point, again, I will have 6 situations happening, yes? So this means that this 6 is independent of how I have done the first stage. So this means that the product rule is applicable. So this question mark is just 6 times 6, which is 36. Is that understandable? I was thinking a little bit, so might be I think this is better, but I was thinking in this way. I was thinking that, okay, let us concentrate on one of these squares, 3 by 3 squares, and I project this square, I project it onto the y-axis. The shadow will give me 2 points. The shadow of this line becomes this point, the shadow of this line becomes this point, yes? And then if I do the same thing here, the shadow of this one becomes this. So let me clean this, and then this becomes this. So it means that my task was this: to choose 2 points on the vertical axis and 2 points on the horizontal axis with distance 3. That's also possible. Yes. And then how many ways I can choose these 2 points? So you see, 1 way, 2, yes, 3, 4, 5, and finally 6. Yes, and the same thing here. So I can have these pair of points chosen in 6 different ways, and again, might multiply them, it becomes 36. But that's okay. But this is the take-home lesson: is this: this was not exactly clear that this problem is a two-stage task. If you just want to randomly multiply some numbers together, it doesn't work. You should have a strategy. So you see, the answer to this problem is an elementary primary school problem, yes? 6 times 6. But don't think that because the answer is so simple, coming up to that answer is also simple. This is the nature of combinatorial problems. The solutions then expressed are very, very elementary, but coming up to that answer could be quite hard, yes? I will try to give you some examples of that kind. But so this is also a problem of a completely different nature that we talked last time. Just I wanted to bring this up. Okay, now I want to ask you a question. Can you just tell me, if I want to talk about tasks that can be broken down into 3 stages, so how can you express the generalization, the extension of the product rule from 2-stage tasks to, for example, 3-stage tasks? Is the question clear? So I want to just give me formally, how do you express yourself? Last time I wrote some long sentences for you that I was describing the product rule for the tasks that can be broken down into 2 stages. Yes? Now I'm asking you the question. I want to write the product rule for the tasks that can be broken down into 3 stages, not 2. For example, if I ask you to write me a 3-digit number, you cannot finalize it in 2 steps. You have to decide about the left digit, middle digit, and the right digit. Yes? So this is a task that cannot be accomplished in 2 steps. It has to be accomplished in 3 steps. How do you interpret? Yes?
I think that about it, like we could pretend that doing the 2nd and 3rd steps are one big step.
So that idea is good, but I want to break it down into 3 pieces from the beginning. Yes. So I don't know. Have you written down my statement for product rule from the last? Yeah, bring it in front of you and try to read those sentences again and make amends to it. Whenever needed, change something. Okay. So what was the first statement? Can you just read it loud, please?
Consider a task whose accomplishment can be broken down into 2 stages.
So now instead of 2 stages, you write 3 stages. Okay, and then?
If the first stage can be done in n sub 1 number of ways.
Yes.
And independent of how the first stage is done, the second stage can be done in n sub 2 number of ways.
Up to here is exactly the same. And now, can you make the difference now? And independent of how you complete my sentence.
Of the first and second stage.
Exactly. Independent of how the first one and the second one are done, the third one can be done in n sub 3 ways. Yes? Then in total, how many ways I can do it? N1 times N2 times N3. Yes? So here, if I have a 2-stage, thank you for cooperation. You didn't talk at all. Yes? Do you understand what's going on or not? Yes or no? Yeah, okay. So here, so I have a task now. This can be broken down into 3 stages. The first stage can be accomplished in any one of these N1 possible ways. But the second stage, independent of how the first stage is done, can be accomplished in two different ways. The third one, independent of how the first one and the second one are done, can be done in n sub 3 ways. Then, to accomplish the task, I have this number of different ways. Yes? So let us just repeat it for a task with 4. If a task can be decomposed into 4 stages, and the first stage can be done in any one of these ways, A stage 2, independent of how stage 1 is done, can be done in n2 different ways. A stage 3, independent of how these two have been done, can be done in n3 different ways. And a stage 4, independent of all the previous ones, can be done in n4 ways. Then the task can be accomplished in the product way of these, yes? So that is the way that you need to think. It becomes harder, but so whenever you want to write a number here, you need to check the independency of this number from the previous steps. Okay? So if that is the case, then you can actually use the product rule. Yes? General more or less is the same. Yes, but it would be a very long sentence. Yeah. Yeah. Okay, so but you understand what I mean. So I don't want to spend time on it to write it very officially because it is very simple at the end. What you gain is not that much. Okay, now let me just try to give you very simple examples as before and then go forward. Okay. So consider these. This example. So how many, number one, how many 4-digit numbers are there? Number two, how many of them have all their digits distinct? So number three, how many 4-digit odd number with distinct digits are there? Yeah, I don't want to spend so much time on them because I know that they are very, very simple. But here I am talking about the task that can be broken down into 4 stages. So these are very, very E-level questions at this point. Okay, so this problem is very simple. Let me solve it for you. But then this is very common in combinatorics. You really don't need to write all these details, even though you have to think about that. So let us solve number 1. I want to write a 4-digit number, okay, without any restrictions. So it means that I can consider 4 positions, yes? Position number 1, position number 2, position number 3, position number 4. This is easier because if you want to write all the details in words, it's really time consuming and it's not worthy, yes? So you say that, okay, I want to write a 4-digit number. It means that I have 4 distinct positions. I want to fill it up with the digits possible. And then we know that the numbers that you can use here is 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9, yes? These are the numbers that I can use here. Okay, for example, which one you want to decide to be stage 1, which one to be stage 2, that's up to you. But if you remember my recommendation from the previous session, it is better always to prioritize those positions which have some restrictions in them. For example, I would prefer to start from the left-hand side because there is one limitation. I cannot put 0 here, but that limitation doesn't appear in these 3 positions, yes? So, and then I would write the number of elements that I can put here. How many elements I can put here? So you see, don't get confused. This is the position number 1, but it can be filled with 9 possible cases. Okay? And now, how many, this is position number 2, this is position number 3, and position number 4, but how many numbers I can put in? 10, yes? And then, is this 10 independent of how I have done the first one? You need to answer this. You need to train your brain to think all the time in this way. Is this 10 independent of how I have done? Yes, because it doesn't matter which one I have chosen. I still have 10 options available for the second one. But how many are there here?
Again 10.
Again 10. And this 10 is independent of how I have done this and how I have done this. And again, this is 10. And then you just write 9 times 10 times 10 times 10. If the number is easy, you just write it down. Otherwise, just leave it as a product. You can just simply answer 9 times 10 times 10 times 10, and that's acceptable for me. Because the point is not the final number. The point is how you calculate this. So the answer is 9,000. Is that clear? Very simple. Let us do the other ones very quickly. How many of them have all their digits distinct? So again, I will draw something like this. First position, second position, third and fourth position. Again, this is a stage 1, for example. I have 9 of them. Okay? But how many options are available here? When you say 9, it means that you have chosen one of them, but because the repetition is not allowed, you need to cross it over. Which one, we don't know, but does this affect the number that you put here? Yes or no? Yes?
It does, but you also gain 0 as a possible choice.
Yes, so it becomes again 9. Yes? Because you don't know which one you have chosen here. Assume that you have chosen 1. You are not allowed to choose 1 again because repetition is not allowed. So you take 1 away. But now because you are writing the second digit, you still can use 0. So again, you have 9 options available. And this 9 is important. It is independent of how you have done. For example, if you have chosen 3 in the first place, then still you have 9 options available. So this 9 is independent of how I have done this. When I go to here, how many options are available? 8, because now 2 of them are crossed over, yes? And then, of course, I can use 0. So this is 8. Is this 8 independent of how I have done this and that? It's clear. 2 of them are crossed over, so there are only 8 left for me. And what is the last one? 7. What I am telling you, when I say that I don't need any calculator in the exam, you just write this answer for me. That's it. Okay, you don't need to do it unless I explicitly mention that, okay, you can use your calculator. But that answer is completely enough for me to get the points of this. How many 4-digit odd numbers with distinct digits are there? I don't know why I have this. Okay, so now we go here. So 1, 2, 3, 4. 100% guarantee that you can start with which one, but you need to learn. Might be sometimes by changing the order you can solve the problem. So which one do you want to choose as stage 1? And which one do you want to choose as stage 2?
I would choose the rightmost digit.
There are more limitations there. This is just a rule of thumb. It might not work. Okay? But because I have more limitations here, so let me put it as stage 1. And then let me put this one as stage 2, and it doesn't matter, apparently. We don't know. Sometimes we have to do trial and error. Stage 3 and stage 4. Let us try to see this. If it works, we are done. If it doesn't work, it might happen rearranging the order will work. And most of the harder problems is that no. Even if you rearrange, it is not enough to apply the product rule. Yes? Let us check. So my goal is to write a 4-digit odd number with distinct digits. I have this one. The simple task is the first stage. How many options are available there? 5. 1, 3, 5, 7, and 9. So I would write 5 options are available. But one of them is crossed over. because there is no repetition allowed. So for example, let me just cross this one over. And let us jump to stage number 2. So how many options are available here? 3 is already crossed over. About 0, I know that I cannot put 0 here, so I don't cross it over, but I ignore it for this stage. How many options are left? 8. Okay, for example, let me take this one out. And then I just show this again. How many options are available here? By the way, is this 8 independent of how I have done here? Because it doesn't matter if I have crossed 5 instead, again I have 8 options. If I have crossed 7 instead, still I have 8 options available. This you have to check. We go to stage number 3. How many options are available here? Yes? Again?
Yeah, because we gained 2.
Here now 0 can be had. So it is again 8, yes. Agree? Now let us cross one of them over. Even 0 can be crossed over here. But how many options are left here now? 7. Be careful. You need to check. Is this 8 that you have written here independent of these 2 stages? Is this last number that you have written is independent of these 3 stages? Be careful. You need to try to all the time check this. If this is not the case, and it is really elusive, sometimes you even experienced people can make mistakes, and then this will give rise to double counting. So you count something, and when you go to faucet, you see that what you got is much more than what is written in the faucet. Because if you don't care about this, you will start double counting. You are counting something twice or 3 times. So this is very, very delicate. Okay. So it seems that this worked actually. So this means that you answer 8 times 8 times 7 times 5. Let us double check. 5 times here, so I cross one of them over. Then I come here, that is crossed over, 0 cannot be chosen. I have 8 options available. When I go there, so one of them is also crossed over, say 6, but when I go here, still 0 can be chosen. So I have 8. So one of them is also crossed over, I have 7. So everything is correct. Yes? But for example, let me change the order of these stages. Okay? Let us check the natural order. The natural order is that writing from left to right. Yes? So why this doesn't work? So if I take this one as stage 1, if I take this one as stage 2, this is the natural order, yes? Because when you want to write a 4-digit number, you start writing from left to right, yes? So why this is not working? I ask you, how many options are available for S1 this time?
9.
9, because the 0 is only the limitation. But how many options are available here?
9. Okay.
Yeah, it seems 9. How many options are available here?
8.
8. But can I say how many options are available here now? It depends which numbers have chosen here. So this means that the natural order is not good for counting. It's good for writing, but not for counting, yes? So this does not work. So be careful again, I'm repeating. Sometimes changing the order of stages will help you to solve the problem in one step. But sometimes more harder problems, it doesn't work. Even if you do this, okay, it doesn't help you to solve the problem in one step. Then you have to count different parts and then add those parts together. So that would be the content of the sum rule. Any questions here? Yes? Okay. So this is one. Let us now go to set theory. The good questions are this. Do you remember these are very important questions from combinatorics and set theory together. That's also part of your book. So do you remember if I have a 3-element set, how many subsets are there? When I was teaching you the set theory, I told you that there is a formula. Take it for granted, yes? 2 power 3, yes? Now can you tell me why? If I ask you, I have a set with n elements, how many subsets are there? You would say 2 to power n. Okay? I told you take this for granted, but I will prove it for you when we study actually the product rule, and now this is the time. Okay, so let me by the way, this is my advice for you. I really like this subject a lot because you don't need any prerequisites, but it could be very, very hard to solve. Okay, so I have worked a lot on this combinatorics. So this is my advice to you. I would say that for simple problems, if I give you this and I ask you to write a subset, I am completely sure everyone in this class can write a subset. For example, can you give me a subset? But my claim is that if you can write the subset, you can also be able to count it properly. The only thing that you need to be careful is to go to your brain and see how your brain processes this problem. Okay? When I say, by the way, when I say to write, one of you, can you raise your hand? Who wants to give me a subset of this set? Yes, please. Okay, you gave me the extreme one. Okay, that's also correct. But I will come back to you how your brain decided about this. Yes?
BC.
BC. For example, you say B and C. But let us analyze Khulud's example first and then Alex. Yes, that's right?
No, Carl.
Carl, sorry. Yes. So Carl, how did you come to this empty and how did you come to A, B, and C? For example, can you just think a little bit about what happened in your brain? You can cook up a story.
I figured out that B and C is a part of A.
Yes.
A, B, and C.
I would say probably you did better than that, but you did it very quickly that you don't recognize that. How did you choose B and C? I don't know. Might be, I don't know what happened exactly in your brain, but you started taking decisions somehow. Do you agree with me? For example, you just looked at these three elements. For some reason, might be you don't like this form of this artistically. You just throw this away and then decide to choose B and C. This is a story I'm cooking up, but it isn't probably have some reality to it. Yes. So when you saw these three, you decided about A, you decided about B, you decided about C. You decided that A shouldn't be in my subset. You decided that B has to be in my subset. You decided C has to be in my subset. Yes? And Carl, what you did?
I thought about the smallest.
So you didn't like anything, yes? Yeah. So you didn't like any one of them at all. So you decided, let us get rid of all of them. Yes? I didn't like A, I didn't like B, I didn't like C. Something like this, yes? That's exactly what you are doing. You are choosing something and choosing something to be in your group, choosing something not to be in your group, yes? You are actually deciding about this. And now I am asking you, when you want to choose about A, how many options are available? You want to make a decision about A. Let it be in your team or let it alone, okay? So you have two options to decide about A. Yes? Leave it or keep it. You decided to leave it, but you have two options available when you looked at A. You had two options available when you looked at B. You had two options available when you looked at C. So in principle, how many options are available? This task is a three-stage task. You decided about A, you decided about B, you decided about C. How many options are available when you want to decide about A? Two options. Yes? How many options are available for B? Two. How many options are available for C? Two. So then the product rule tells you that there should be 8. Is that understandable? Yes or no?
Yes.
This is one way of counting, which is very simple, but you need to train your brain to think in this way. Another one is called one-to-one correspondence. One-to-one correspondence is also very, very powerful technique in combinatorics. It's really powerful. I will give you some examples when we go through the lesson. Another one is that instead of counting this, I count a different setup. But I convince myself the number of elements in that new setup is equal to the number of things that I want to count here. For example, let me ask you a completely different question. I give you two numbers, 0 and 1, and I ask you to write all possible 3-digit codes, 3-digit binary codes, not numbers. How many 3-digit binary codes you can write with these 0 and 1? Of length 3. Let us write all of them. Yes. One of them is 0, 0, 0. Agree? The other one is what? 0. So let me write 1, 0, 0. Another one is what? 0, 1, 0. I don't know. One of them is 0, 1, 1. These are the different codes. Can you count this one? This is for, I don't know, for our brain, counting this is easier. So if I ask you how many codes, 3-digit codes I can write with only 0 and 1, how do you count it? You say that I have 3 positions to fill up. How many options are available for the first one? 2. How many options are available for the second one? 2. Because 0 or 1. These are the only options, yes? And how many options are there? 2. So how many codes, how many binary codes with 0 and 1 of length 3 I can write? 8. Yes? Is that understandable? Now, this is totally different from that problem. But a one-to-one correspondence, you need to cook up a story. You should be a very good storyteller, yes? You need to find a connection to prove that this number is exactly to that number, okay? I would say this. I would say that, okay, when I see, I have 3 places here. I put them here. And then I distribute these codes below them, okay? If the number below that one is 0, it means that I don't put it in my subset. Yes? And if the number below that is 1, then it means that I put it in my subset. Okay? Now, for example, calls code. What is calls code? 0, 0, 0. So you see, 0, 0, 0 is something here, but it gives rise to this one. Yes? And then what is Khulud's one? 0, 1, 1. So this is the code that corresponds to this subset. So you see that this is a very, very powerful tool. It means that I need to be a little bit smart to cook up a new problem, which is easier for me to understand it at the abstract level, but I can convince myself there is a one-to-one correspondence between the number of items in this new problem and the problem that I want to solve. This, if you can convince yourself of that, then instead of counting this problem, you can totally forget about this problem and solve another problem. Because here, the important thing is the total number at the end. We don't want to see, we don't want to have a procedure to count it. Is that understandable? Okay, so let me write it here. Let me make it clear. You see, let me put a bag here. Let me write all of the sets. Let us practice. This is this one. Do you remember? This is this one. Another one is this one. Another one is this one. And the other one is this one, and this one. Oops. A and C. And finally, the whole thing. Yes? Okay. Momentarily forget about this. And I have another bag. In that bag, I have all possible codes. Yes? All possible binary codes. This one. And then I don't know, 1 0 0 0 1 0 0 0 1 1 1 0 1 0 1 0 1 1 and finally 1 1 1 1 2 3 4 5 6 7. Yes, and then instead of counting the items in this bag, I momentarily count the number of items in this bag. But then I find a one-to-one correspondence between them by this rule. So that is my rule. I say that these are corresponding together. So can you tell me which one is suitable for this? Which code? Exactly this one, yes? So this one, let us see. Which one is this one? Yeah, I don't know. I accidentally wrote them in order. So that is also this one. Yeah, that is also this one. I am really unfortunate. But anyway. So, but what is B of C? B and C? 0, 1, 1. Yeah, this is this one. And then what is this one? This one, yes? And then finally this one. Do you agree? So this is a very powerful tool. I want to talk a little bit about that. So shepherds, I have heard actually in Iran, there are people that are not, couldn't actually count at that time. Okay, very, for example, 100 years ago. And the trick that they use is that the number of ships that they have small sticks for one-to-one correspondence. So the ships when coming back, yes, the person didn't count the number of ships, because if he could count, he knows that, okay, he has 100 ships, and then sheeps, actually, not ships, yes, sheeps are coming. There is no sheeps, yes, I should say sheep. There is no plural for sheep.
It's just,
Yes, is that right or not?
Yes.
Sheep, okay, sheep is both plural and singular, yes, okay, anyway, let us talk about goats. Okay, it's easier for me. Okay, so that is actually, if I know how to count, I say that, okay, I count the number of goats, so I know that none of them is dead and none of them has actually have a new baby, okay? So I have the same number of goats. But if I don't know how to count, I can do this trick. I can have, I don't know, sticks in my hand, little sticks in my hand, corresponding to each one of these goats, yes? And when the first goat go in, I take one of them and put aside, okay? And be careful, I don't know the number here, but I can find a correspondence between the number of goats and the number of sticks in my hand. And it doesn't matter what I am counting here. This is a really powerful tool. You might a little bit underestimated that, but let us talk a little bit about infinities. That is also fun, yes? So, for example, if I ask you, consider the set of all odd natural numbers and consider the set of all even natural numbers. Yes? Okay, so let me call it odd numbers, the set of odd numbers 1, 3, 5, 7. But how many of them are there? It's infinitely many. Yes? And let me write even numbers. So this is 2, 4, and then 6, and then 8, etc. Yes? Of course, if I ask you, do you think there are same number of elements in O and E? What your intuition tells? Of course, if I ask you, if you say yes, then I ask you how many of them are there, you should say infinity, and how many of them are there, you should say infinity. But is it enough to say because this is infinity, that's also infinity, they have the same number of elements in them? Yeah, you need to, I don't know, but let us talk about the set of whole natural numbers. 1, 2, 3, 4, 5, 6, and etc. Now, what is your intuition? The number of elements, of course, here is infinite. Here is infinite. It is also infinite. Yes? But what do you think? Is the number of elements here somehow bigger than the number of elements here? Bigger than the number of elements here or not?
No.
Yes.
Yes or no?
Yes.
So what do you say, Alex?
I say no.
So what is the number of elements here and there?
Both infinite.
Okay, both infinite. Okay, but then let us talk about R. That's also infinite. So I just want to understand you. This is completely optional, but this is very interesting. I want you to understand about this. So what is your guess about this? Is there more number of numbers here than here and there? Yes or no?
First 3 are equal, and the last one is the bigger one.
Yes, we have to admit the number of elements here, here, and here are the same. Yes, but not for the last one. Last one is much bigger. Okay, let me convince you, but try not to resist the logic. Okay? And that is exactly the notion of one-to-one correspondence. Yes? So do you agree that if in a room there are some number of chairs and there are some students outside, and I ask the students go inside and each one of you take one seat and sit down. Yes? When I come, I don't know how many chairs are in the room. I don't know how many students are there. But I come to the class, but I just see that every seat is occupied by one student. No student is standing up. No seat is empty. can I immediately conclude that the number of chairs and the number of students are the same?
Yes.
Yes, is that right? Is that understandable? If I come here and I see that some chairs are empty and there are no chairs that 2 students are sitting in one chair, what can I conclude about the number of chairs and number of students?
More chairs and
More chairs, yes? So it is completely logical. And if I come here and I see that all seats are occupied by 1 student, but there are some students standing, what can I immediately conclude? More students, yes? In this idea turns out to be exactly, because we don't know how many. In this case, there is another way. I can count the number of students because I know how to count, and I come to the room, I count the number of chairs. If these numbers are the same, I can conclude that they are the same numbers. If they are not, I can see which one is bigger. But this first idea does work for these cases, but counting does not work. Because how can I count the number of elements here? There are infinitely many elements. I cannot count them, but I can think to attach them together, okay? So for example, let us talk about this and that. Let me show you that the numbers of elements in these 2 cases are the same, okay? Exactly like this, I want to do like this. I consider 2 bags. In one bag, I want to write 2, 4, 6, 8, I don't know, 10, 12, and continued forever. Okay? And then I have to sit down in that chair. Okay? So what happens if if the students actually obey me, this student divide this number by 2, what will find? It will find 1, and then he will go and sit on chair 1. Yes? And then this student will go and find chair number 2. And this student will go and find chair number 3. Now my question is that, do you think that any of these students will be without a chair at the end? Is that possible that this happens? No. Do you agree? Every student has an even number. They divide it by 2. You divide a natural number by 2, it becomes a natural number. An even number by 2, it becomes a natural number. So it means that all these people will find a chair to sit. Okay? But another thing, this is not enough. Might be the number of chairs is much more. Yes? If the number of chairs is much more, of course everyone can find a chair to sit. But this doesn't mean that they have the same number of elements. But let me say, you might say that there are more chairs than students. Do you believe in that? Are there more chairs than do you agree that there are no more students than chairs? Is that understandable? Because every student divides the number by 2 and find a chair and go and sit down there. So it is clear that it is enough chair for students. But are there enough students for chairs? How do you know that? How do you know that none of these chairs will be left empty? Yes?
Because if the chairs think and they times their number by 2, then they would find a corresponding.
Exactly. So if you say that one of these chairs is empty, which one? For example, do you believe chair number 500 is empty? No, because which students has sat there? No, 2 times larger. 1,000. Yes, 1,000 has sat here. Yes, and then, for example, I don't know, 121. Is this chair empty? No, the student with number 242 has taken this chair. So I don't know, do you understand? This is a very powerful tool. So this should convince you that the number of chairs and the number of students are the same. On the other hand, these are coming from this set. These are coming from this set. Apparently, we think that these should be twice as large as this, but it is not. Is that understandable? So working with infinities is very counterintuitive. Everybody happy with this argument? If you're not happy, you are resisting the logic. Yes? Any questions? You're not happy?
No.
Okay. So what about Z, by the way? But cooking up this one-to-one correspondence can be extremely hard. It doesn't necessarily mean that I can cook up any story that I like. I cooked up a story, it worked, okay? And the hard thing is that if my story doesn't work, it doesn't mean it is not true. Okay, so might be some other one can come cook up in a story which is much wiser than this one. And then this turns out that what about Z? Which has more number of elements there? Z or N? Z includes the negative numbers, but N is only positive numbers. Yes?
I still believe they're the same.
They are the same. But if you want to have a story for that, can you find a corresponding rule? So what is the corresponding rule here? Can you tell me? X goes to X divided by 2. Yes? So this means that I can look it as a function. F of X is equal to X over 2. So this function is the rule for this assignment. Yes? Finding a function that assigns N to Z, you need to be a little bit more creative, but not hard. Can you cook up the story? -1, does it work?
Because like -6 out of 6, -5.
Okay, but this argument works in one side. Do you remember here?
No.
I told you
No.
yes.
No.
Because, for example, let me just put one N. You say that you multiply by -1.
-6.
No. Let me tell you. You want to send 1 to what?
Means the plus.
No, I know. So you tell me, okay, this is the number of students, 1, 2, 3, etc. And for some reason in the room, I have labeled them with 0, +1, -1, +2, and -2. Let the students sit down. How do you send them in? According to your rule. So you are saying that the student number 1 go and takes which seat?
His number multiplied by -1.
So it is -1, you mean?
Yes.
The student who has this number
Yes.
will go and sit here.
Yes.
The student which has number 2 will go and sit -2. Do you agree? Yes. But which student? So, and then you continue forever. What you get here, what you get? You get all negative numbers.
Yes.
So, but there are other chairs here as well. They are empty now. Do you understand what I mean? Do you understand? Because this rule works. It means that every student definitely will find a chair to sit. But this doesn't tell you that the numbers are the same, because it might be the case that there are many more chairs. In your case, yes, there are many more chairs. If you send the students in this way, completely correct. Every student will get a chair to sit down, but all the chairs with positive numbers will be left empty. Okay, so it means that you are in a limbo situation. You haven't proven something, you haven't refuted something. You understand what I mean? So the rule is a little bit more complicated if you want to do this. Yes?
Sure.
Yeah?
Just as an example, all negative numbers take the inverse odd number, while all positive numbers take
What do you mean?
the even numbers.
Inverse, you mean opposite.
I split up the ends into odd and even.
Yeah, that is more or less the correct idea. But you said inverse. Inverse in mathematics,
Sorry, I mean the negative.
positive. Opposite, yes? Yeah, that is the good idea. So if you want to have a practice, I really recommend you try to find a connection. So, yeah, but this rule was good, but this rule goes from one direction. You need a rule that goes into two directions. For each one of them, there is one and exactly one from here. For each one of them, there is exactly 1 and 1 from here. If you can find this correspondence, then instead of counting, you can immediately say that the number of elements here and the number of elements there are the same without counting them. Is that understandable? Okay. So this idea of one-to-one correspondence is extremely important in combinatorics. Of course, you need to be very smart to change your perspective from this problem to a more abstract problem. Because in combinatorics, usually abstract problems are easier or more fit to what we want to do, yes? Okay, so this one, now let me ask you one question. This, I don't know, for some reason, based on my experience, this is psychologically a little bit hard for students to understand. So I have I have 30 chairs. 1, 2, 3, up to 30 chairs. They are labeled from 1 up to 30. And then I have 5 students. Okay? Do you have questions?
I think I have a function for both rows.
For this one? For Z and N?
Yes.
Yes?
If your number is n, does n minus 1 over 1 to the power of n.
What? So you say from N to Z or the other way around. How do you want to write your function? Takes an N element from here, give me an element from here, or the other way around?
Say your number is k. So your next seat is k minus 1 to the power of k.
To the power of k.
No.
It's without parentheses. So the k belongs to the 1.
Aha, okay. So you mean something like this?
No.
Without the minus.
Ah, you mean this.
No.
So this is
No.
multiplication, you mean?
No other minus.
Without multiplication.
K minus parenthesis only 1 without the minus.
May you repeat?
K minus parenthesis without the minus inside the parenthesis. Yes.
Remove that.
Remove it.
Yeah.
So what is the point of this? That's why I'm confusing. Yes? Because 1 to power k is always 1. Why do you write 1 to power k? Do you understand what I mean? That was why I was confused. Because this makes sense. Because if it is positive, so it means that this becomes a k plus 1, k minus 1. But if you write k minus 1 to power k, it is always equal to k minus 1. So you don't need to put that k up there. No, but the idea...
I meant the one that you said. That's right.
So even this one, I don't think why, because this sometimes gives you a k plus 1, sometimes gives you k minus 1. No, I don't think this is correct one.
Just about like you
Yes.
have to use the brackets where you say like if la 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 then la la la, or is it possible to construct one single function?
No, I know one single function. Might be some other people can do another function. But you need to prove whatever function you choose, you need to defend yourself that this is a one-to-one correspondence. I'm not saying, and this is not that easy all the time. Yes, but one of them is enough. If I can find only one-to-one correspondence rule, that is enough. Yes. Okay, let me ask you this question. There are 30 chairs in this room, 5 students. How many ways I can distribute the students in the chairs? No, don't think. So try to train yourself. You need to say, what is my task in your brain, even if you don't want to tell it to me, keep for yourself, okay? What is the task here? How many steps are needed to accomplish this task? Can I apply the product rule? These are the common mistakes when people come to combinatorics. They want to give you the answer immediately. The final answer, I agree, is super simple. But getting to final answer could be quite super hard. Yes, but of course, this is not super hard in this problem. Anyone else? Just think that you want to do it. Is it possible that you cannot manage it? Assume that you are responsible for primary school kids, and there are 30 chairs, and then you have 5 kids. Don't you really know how to distribute them? Is it possible that you don't know that? Definitely everyone can manage that. If you can manage that, think how you think when you are managing it. Yes?
I choose a student and a chair.
Okay, really. So for example, you have one student here. So if I wanted to do this, might be I'm a little bit experienced. I said that, okay, wait in the queue. I call the first student. I see him or her. And then I say that, okay, go and sit down in that chair. And the next student come in, I do that. Okay, think in this way. This task is accomplished if I have given every student a seat. So how many stages are there for this task? How many stages? 5. I have 5 students. I have to give them place to sit. So how many possibilities are there for the first student coming in? 30. How many possibilities are there for the second one? 29. How many of them are there for the next one? So ask yourself, why didn't you come up to this answer? Otherwise, this topic would be extremely hard for you. Okay? If you don't think in that way. So the answer to this question is 30 times 29 times 28 times 27 times what? 26. 1, 2, 3, 4, 5. Leave it like this. That's the answer. I don't want more than that. I just want you to write this in the exam for this question. But I don't know. I hope that you are convinced somehow. Coming up to this answer might be a little bit confusing if you don't know how to start with. Okay? Let me change the question. Let me now change the question. Now I have 30 people, but I have only 5 chairs. In how many ways I can let them in and sit down in a chair? Of course, there are not enough chairs for everyone. I have 30 people outside, 5 chairs in this room. In how many ways I can do this? Now let everyone think. By the way, this is the exam question, something like this. As simple as that.
What is the task again?
The task is that I have 5 chairs in the room, 30 students outside. In how many ways I can let them in and sit down in a chair?
All of them.
How is that possible? No, every chair should be taken care, should be occupied only by one person. It is clear that some of them will not have seats, but the situations are different. This is my advice. You need to think, I don't know, imagine like a director of a movie. Think what you are doing. If you don't define your task, it is useless. I don't accept it from you. Think you really want to do that. For example, some of the students are your friends. You want to let them in and sit. This is one possibility. One possibility is that, is it completely fair? You just take a lottery and see who wins and they can sit. Anyway, you should cook up a story. Really, you need to cook up a story. Yes.
Sorry, can I say?
Yes?
You put all the chairs in a stack, then you take out the topmost chair, and then you throw it at somebody you don't like.
Exactly. But we don't, as humans, we don't do that. Mathematics doesn't care about chairs if you are a chair or if you are a human. From mathematical point of view, both of them are objects. It doesn't matter if the chairs are here and I put the people on chairs. Mathematics doesn't care. You can put the people here, put chairs on top of their heads. So I don't know. I don't know. By experience, I know that for us, solving the first one is easier than the second one. This is a psychological probably idea. But do you agree with me? These are objects. From mathematical point of view, humans are objects. Chairs are also objects. So in the first case, I have 30 objects and 5 objects. In the second case, again, I have 5 objects and 30 objects. So the answers are not the same. But if you are not convinced, let me convince you in this way. I would say that, how many tasks did I have here? I have one task, but I can split it into 5 parts. I would say that a stage 1, can you tell me what is a stage 1 in this case? In this case that I have 36. Yes? Right. Choosing a chair assume that you have person A, B, C, D, E, 5 persons. Choosing a chair for A. Yes? S2, choosing a chair for B. Yes? Can you tell me how many choices I have for this S1? 30. I have 36. Yes? How many options I have here after this person has been taken the place? 29. And then this is why I come to this answer. Yes? Now, assume that I have only 5 chairs. I have 5 chairs, but 30 people. Let me call them like this. Okay? Now, can you tell me what should I write for a stage 1? Yes?
Choosing who gets to sit in chair 1.
Exactly. Choosing who should sit in chair 1. Yes. Choosing a person for chair 1. You see, choosing a person for chair 1. Yes. Choosing a chair for person 1. Here, choosing a person for chair 1. Yes. That's not different. How many ways I can do this again? Again, 30. But I don't know. Psychologically, you are more closer. You have a higher chance to answer this correctly. But when it comes here, I don't know, for some reason you think that they are different. Yes?
So isn't there the option to not put the person in a chair
Here?
for the second one?
No, yes, that is correct. There are no enough space, but what is the case then? What's the problem then? Choosing a person for chair 1. It means that for some reason I like this person, I give this chair to that person, I just throw this person away. But you might come in and you like this person, you dislike this person, you give this a chair, but not that one. No, it is completely this universe problem. It's very simple problem, so don't get confused. Yes? As simple as that. People are standing, you want to let them in and sit down. Yes? But what I'm trying to say, for me, it is better to understand that from a mathematical point of view, there is no difference between humans and chairs. Both of them are objects. Yes? And I am distributing 5 objects in 30 boxes. Yes? Let us look at it in a different way. I have 30 boxes and I have 5 distinct colored marbles. I want to distribute them here. This is the number of ways that I can do. Or I can do it the other way around, yes? I can choose the marbles and choose a place to put them in. Okay, psychologically, we usually put marbles in the boxes, but not boxes on top of marbles. Yes? But if you don't like this idea, you need to write it down explicitly. I really recommend you to go sit down and understand this problem. Be patient and consider both scenarios and write the sentences properly. Yeah, don't be lazy, write it. I can show you my scratch papers, okay? How many scratch papers I have in 1 year, okay? It's more than 1,500 pages, okay? So don't think that you should, even though I know these things, but sometimes I come to a new idea when I am just writing them down. So please go home and write this down, okay? If you don't do that, then of course, there is no high chance to learn mathematics in a very good way. So you need to be able to do this. Any questions here? Yeah. Okay, so I think we can stop here. If you don't have any question, we can stop here. Next week you are not here, so we continue in Zoom, not on YouTube, okay? Because there would be a delay between your questions and my answers.